Let's welcome Christopher Hojny from Eindhoven University of Technology, and he is going to talk about computational aspects of relaxation complexity.
Yeah, thank you for the nice introduction, and I would also like to thank the organizers for the great opportunity to speak at this nice and great workshop. And in this presentation, I want to talk about ways to compute the relaxation complexity of a set of integer points, which is joint work together with Gennady Avakov and Matthias Shimura. But of course, before we can start talking about how to compute the relaxation complexity, let us first define what the relaxation complexity is. And to motivate this, suppose we are given a combinatorial optimization problem, and we want to solve this problem using linear programming techniques or integer programming techniques. Then, of course, the first step that we have to do is we have to encode our problem using certain integer points. And if we want to use linear programming techniques, then we basically have to compute the convex hull of the set of points that we are interested in. And we can solve our problem, for example, using the ellipsoid method or the simplex algorithm. If we do so, we can, however, observe that in general, we need exponentially many inequalities to describe the convex hull of our sets of points. And for this reason, one has also investigated extended formulations in which we are allowed to introduce additional variables and to try to describe the convex hull in an extended space with the aim to reduce the number of inequalities. But still, there exist examples that we need many, many inequalities. And in this presentation, because it's the MIP workshop, we want to talk about integer programming techniques. And we want to actually find out how many inequalities do we need in an integer programming formulation of our set. So we do not want to describe the convex hull precisely anymore. We just want to separate the integer points in our feasible region from the remaining integer points. And the relaxation complexity is then the minimal number of inequalities that we need. Let's make this more precise because, of course, not every set of integer points admits such an integer programming relaxation. For the rest of the talk, we assume that we are given a polytope P that contains the integer points that we are interested in, or the integer points contained in this polytope are exactly the points that we are interested in. Then we know that there exists such an integer programming formulation just by taking an outer description of our polytope. And in the following, we call any such set X a lattice convex set, because if we take the convex hull of the set X and intersect it with the integer lattice, then we can recover our original set of integer points. And using this notion of lattice convex sets, Keibel and Weltke introduced the notion of a relaxation of X, and they said a polyhedron Q is a relaxation of the set of integer points X if the intersection of Q with the integer points leads again to our set of points X. And the relaxation complexity is then the minimal number of facets in any relaxation of X. Equivalently speaking, if our set of integer points is full dimensional, then the relaxation complexity is the minimal number of inequalities that we need to separate the points inside our set X from the remaining integer points. But maybe this is a very strict requirement, and throughout this talk we will also consider the situation where we only want to separate our sets of point X from some set of infeasible points Y. And then we denote the minimum number of inequalities needed to separate X from the integer points that are contained in Y but not in X by RC of XY. And this relaxation complexity of X with respect to this set Y is then, of course, a lower bound on the relaxation complexity of X because it's less restrictive. Another quantity that might be useful and that we will also explore throughout this presentation is the rational relaxation complexity denoted by RCQ of X. And this restricts the definition of the relaxation complexity to rational polyhedra, or equivalently speaking, to separating X and the integer points that are not contained in X by inequalities with rational coefficients. And then, of course, the rational relaxation complexity cannot be smaller than the relaxation complexity because it's more restrictive. But good news, at least these two quantities, the relaxation complexity and rational relaxation complexity, they are finite, because we can find a trivial upper bound just given by the number of facets of the convex hull of the set X. And in this presentation, I want to focus on two questions that have been raised by Keibel and Weltke. And they were wondering, if we are given a finite lattice convex set X, is it actually possible to compute these values of the relaxation complexity and the rational relaxation complexity? And they were also interested in the special polyhedron, or the vertices of the special polytope, namely the vertices of the standard simplex, so the null vector and the standard unit vectors. We all know that that the convex hull of this set has d+1 facets, but they were actually wondering, is this best possible in an integer programming formulation, or can we save some inequalities? And in this presentation, I want to give at least some partial answers to these two questions. So what we will do first is we want to try to compute the relaxation complexity. To this end, it will be useful to consider upper and lower bounds on the rational relaxation complexity. Then I will turn on integer programming models for computing the relaxation complexity. And I want to conclude the presentation with some numerical experiments that we did. And I want to show how these experiments helped us to also get some theoretical results. So let's start with some bounds on the rational relaxation complexity. And in our experiments or in our investigations, it turned out that it's useful to introduce yet another concept to get upper bounds. And this concept also allows us to robustify the relaxation complexity against small numerical errors. To make this precise, suppose we are given a full-dimensional lattice convex set X, and then we introduce a robustness parameter epsilon. And to ensure robustness, we place around each of the integer points that we want to describe a discrete L1 ball with radius epsilon. And this slightly extended set is then denoted by x epsilon. And we say that a polyhedron Q is a epsilon relaxation of the initial set of integer points x, if this extended set x epsilon is contained in Q. But if we intersect the interior of Q, no new integer points arise. And so this motivates also a robustification against numerical errors. If we slightly perturb an epsilon relaxation, at least the points contained in X remain feasible. And then the epsilon relaxation complexity is the smallest numbers of facets in any epsilon relaxation of X. What we then can immediately observe is that if we are given two robustness parameters, epsilon and epsilon prime, one being at least as large as the other, then the epsilon relaxation complexity for the bigger epsilon cannot be smaller than the relaxation complexity with respect to the smaller value of epsilon prime, because the safety margin becomes smaller and thus we get more flexibility in deriving our inequalities. And using this concept of epsilon relaxations, we were able to derive the following result. Let me first explain, or let me first mention the statement of the result and then its consequences. We were able to show that if we are given an arbitrary positive value of epsilon such that our set X admits an epsilon relaxation, then there exists actually a computable finite set Y epsilon of infeasible integer points such that it's not necessary to separate X from all the infeasible points in an epsilon relaxation. It's sufficient to separate it from this finite set Y epsilon. If we further require that the parameter epsilon is rational, then we can compute this quantity in finite time. And finally, if we are computing the value of the epsilon relaxation complexity for smaller and smaller epsilon, we will eventually find the value of the rational relaxation complexity. And this gives us, in principle, a finite algorithm to find the value of the epsilon relaxation complexity. We take a monotonely decreasing rational null sequence, compute in each iteration the value of the epsilon relaxation complexity, which can be done in finite time by the second property. And then after finitely many degradations of the value of epsilon, the third property guarantees us to find the rational relaxation complexity. The only drawback of this algorithm is, of course, that we don't know when to stop, because it only says we find this value, but we have no certificate for stopping the algorithm. But maybe we can do so later on in this presentation. So let's first discuss why this theorem holds. And let's start with the second property. And assume we have already shown the first property. So there exists this finite set Y epsilon such that the relaxation complexity of epsilon is the same as the epsilon relaxation complexity with respect to this finite set. Then it's rather straightforward to see that we can model this separation problem as a bounded mixed integer program. And if epsilon is rational, all the data in this model will be rational, and thus we can compute it in finite time. And then for the third point, we observe that if we are given a rational relaxation of our set X, then it has to be necessarily finite. Otherwise, there exists a rational ray, and thus infinitely many integer points on our relaxation, which cannot be the case because X is finite. And this shows us that we slightly can perturb our relaxation, turn it into an epsilon relaxation, and vice versa. We can move epsilon relaxations. We can turn them into rational relaxations. So the only open point is how can we show this first point? And to do this, we want to show that actually every epsilon relaxation of our initial set X is a bounded set. To do so, we want to show that we exploit that we can find these L1 balls inside our epsilon relaxations. And if an epsilon relaxation could be arbitrarily large, then we can pick a point inside the epsilon relaxation, Q, compute the convex hull of Q with this L1 ball, and compute its volume. And if this point Q if the epsilon relaxation would be unbounded or can become arbitrarily large, then we can increase the volume as much as we want. But actually this is not possible because of a variant of Minkowski's first theorem that says if we take this red pyramid-like object and its volume is too big, then the number of integer points inside the red polytope will be bigger than the number of points that we want to describe. This is a contradiction, and thus we can show that Q cannot be arbitrarily far away from our set of integer points. From the proof of Minkowski's theorem, we can then also extract distances or estimations on the bounds that we need to bound our epsilon relaxations. And then we can select this set of finite points as the integer points that are contained in the bounding box containing all epsilon relaxations. This is all about upper bounds on the rational relaxation complexity. But what about lower bounds? And maybe lower bounds that we also can use to terminate our pseudo algorithm that we described before. An immediate way to come up with a lower bound on the rational relaxation complexity is to drop the requirement of rationality. And then we can lower bound the relaxation complexity by just selecting an arbitrary subset of infeasible integer points y. And if this set is finite, I've already mentioned it, then we can compute this quantity using a bounded mixed integer program. And this actually suggests to use the following lower bound. So we suggest an algorithm or a procedure in which we fix a parameter t. Then we consider all the integer points whose maximum coordinate entry is an absolute value at most t. And then we compute the relaxation complexities with respect to this box of infeasible integer points. We increase the value of t, and then after finitely many steps, we will find a value that we denote by RC box of x, the maximum value that we can achieve with this bound. And this is then, of course, a lower bound on the relaxation complexity. Of course, we have no guarantee that this bound is matching, but we say that this bound is tight, so the box relaxation complexity is the same as the relaxation complexity if there exists a finite certificate set y such that it holds with equality. In general, we do not know whether such a set y exists, but at least there exist some classes of integer point sets for which we can guarantee the existence of such a finite certificate set. For example, if the convex hull of X contains an interior integer point. So let's summarize what we've seen. We've derived an upper bound that is based on the epsilon relaxation complexity. If we choose epsilon to be small enough, then this is exactly the value of the rational relaxation complexity. We came up with this lower bound, RC box. And if both these values are the same, then we can in principle come up with an algorithm that computes the relaxation complexity and the rational relaxation complexity just by computing these two bounds, and then at some point after finite many steps in the sequences that I've sketched, these two bounds will match and we've found these values. In general, however, it can be the case that this box relaxation complexity is smaller than the rational relaxation complexity, and in these cases we do not know how to compute these values. And for this reason, let's consider in the following the case in which these two bounds match. How can we then actually find the values of the relaxation complexities? Well, and a very naive approach is just to use the procedure that I've mentioned before. We have a counting parameter t. We compute the relaxation complexity of X with respect to this box pt, together with the corresponding relaxation. Then, of course, we can check whether this relaxation is actually a relaxation with respect to the full integer lattice. If this is the case, we found a relaxation of our set X of minimum size. And otherwise, we increase this value of t and iterate the procedure. And at some point of time, we hopefully find the relaxation complexity. And the big question is, of course, how can we efficiently compute this second step? Well, we had a MIP workshop, let's MIP it. And in the following, I want to discuss two mixed integer programming formulations for computing this value RCX of BT. And the first model is a rather straightforward model, and it encodes the inequalities that we need in a relaxation explicitly. And to define this model, we need, of course, an upper bound k on the number of inequalities that we need, because we want to encode these inequalities explicitly. Rho denotes in the following model the maximum absolute entry of a feasible point. And then we also need a sufficiently large constant m. Then we have two sets of variables encoding the inequalities in our relaxations, a for the left-hand sides, b for the right-hand sides. By scaling, we can assume that the a's are contained in -1, 1. And then, because the set x is bounded, we also have explicit bounds on the right-hand sides of our inequalities. Then we also need some indicator variables, SIY, indicating whether the ith inequality in our formulation is violated by the infeasible point y, and UI indicates whether we want to use the ith inequality. Then, of course, we have to minimize the number of used inequalities. The inequalities encoded in A and B have to be valid for our set X. Every infeasible point has to be separated by at least one inequality. If the inequality is declared to be violated by point y, then we need that they are actually violated, and this is modeled using this parameter epsilon. And if we declare an inequality to be violated, we also have to use the corresponding inequality. Putting this together gives us a model for computing the relaxation complexity of x with respect to y if we have this, up to precision epsilon. But this initial model is rather weak, so we enhanced it using, for example, cutting planes. To this end, we observe that if we are given two infeasible points, for example, these two red points here, such that their convex hull intersects the convex hull of the set that we want to describe, then they cannot be separated simultaneously using a valid inequality. For this reason, we can add these conflict inequalities, telling us if we separate one of them with the ith inequality, the other cannot be separated as well. Then, of course, there are lots of degrees in freedom of in this model. So if we have an inequality that is not used, we just fix it to be a trivial inequality. And of course, we can handle symmetries, for example, by sorting the inequalities, first taking the inequalities that are used in our model, and then among the used inequalities, we want to sort them with respect to their first coefficient in the A variable vector. We also considered a second problem, and this model will then be solved using branch and price. To this end, we observe that we can equivalently phrase the relaxation complexity as a covering problem if we consider the points that we want to separate from our convex hull. We essentially compute the infeasible set, the set of infeasible points that can be separated simultaneously from the convex hull of X. And then we can observe that we can find the relaxation complexity by selecting the minimum number of such sets that cover all the infeasible points. And this then, of course, gives rise to a very straightforward mixed integer programming formulation. We introduce non-negative integer variables for each of these sets that we can select. We want that for every infeasible point, there exists such a set in this collection that contains the infeasible point, and then we want to minimize the number of sets that we use in our formulation. If we want to solve this problem immediately, that's of course not possible because there are way too many variables, so we use the branch and price approach for this. Unfortunately, it turns out that the pricing problem is NP-hard. And if we want to embed this into a branch and price framework, we also need a branching strategy. And to do this, we've opted for the following rule. If we are given two fractional solutions that intersect in our LP relaxation, then we pick an element that is contained in the intersection. We take an element that is contained in the symmetric difference of these two sets, and then we create two child nodes by imposing that in one child we want the two red points to be separated by the same set in a solution, and in the other child node we want them to be separated by different sets. And this is inspired by the famous Ryan and Foster branching rule used in bin packing. Of course, we can also combine these two models. We can, for example, just solve the root node relaxation using the branch and price model, and then taking the bounds that we get from this model, transfer it to the compact model, and then running this model with the hope that we can actually save some time because we don't need to call the pricing routine that often. We've implemented this approach in Skip, and we used Simplex as LP solver to solve the LP relaxations. We've considered two test sets. On the one hand, we've considered cross polytopes, and on the other hand, we have considered the standard Simplex. Remember, this is one of the polytopes that we also used in the open question by Keibel and Weltke. And as our test set for the separation problem, we put layers of infeasible points around these polyhedra or these integer point sets at most of a certain L1 distance. And why did we actually go for these two test sets? Well, they are inspired by these two results or questions. The first, the cross polytope, that's inspired by a result by Weltke, who showed that if we take the convex hull of this cross polytope, of the vertices of the cross polytope, then this polytope has exponentially many facets. In a relaxation, however, we needed most 2D many inequalities, and he was wondering whether this bound is tight. And the other is the Simplex, because Keibel and Weltke were wondering whether d+1 is actually the right number for the number of inequalities that we need in an IP formulation. We have conducted some experiments of this, and a quick summary. So we can see that the column generation approach is very, very slow, and this is because the pricing problem is very, very difficult to solve. It's NP hard, and so for this reason we didn't try to find in our first implementation good heuristics and so on. We were just interested in the plain performance of this model when we use it using a mixed integer program to solve the pricing problem. This turns out to be very difficult to solve. So, for example, we can see that for the 5-dimensional cross polytopes, only one instance can be solved within the time limit. All other instances hit the time limit. The compact model is much more competitive, and it can solve 3 instances more. And also, if we compare it for the 3-dimensional Simplex, then the running time also decreases very nicely. But fortunately, what we can also observe is that this idea of the hybrid model is actually very useful, because it's much more efficient than using the compact model or the column generation model on its own. We can solve additional 2 instances for the 5-dimensional cross polytope, and the running time goes down from approximately 1 hour to 5 minutes. But I also wanted to say how we used these results to enhance our theoretical knowledge on integer point sets. And maybe let's consider some of the results. So what we could observe for the cross polytopes is that independently from this radius of infeasible points that we placed around these integer point sets, the relaxation complexity was always d+1. So it is smaller than the upper bound that has been derived by Weltke. And this made us think maybe this d+1 is actually the right number. And it turns out, yes, this is the case, except for dimension 2, the relaxation complexity and the rational relaxation complexity of a cross polytope is exactly d+1. So we can reduce the upper bound by roughly a factor of 1/2. Let's consider the Simplex. Here we could show that in dimension 3, the bound of d+1 is actually correct, because if we take the infeasible points at L1 distance at least 3, then we could show that if we want to separate these points from the Simplex, then we need 4 inequalities. Less is not possible. But in dimension 4, we could observe that independently from this safety radius, or this radius of infeasible points, 4 inequalities were always sufficient to separate all these points. And this made us wondering, is it actually possible that we cannot use more that there doesn't exist a finite set of infeasible integer points, such that we need the proposed or the claimed number of 5 inequalities to separate this? It's always possible using 4 inequalities. And this turned out to be actually true. And in fact, we could even show more. There exist even infinite sets around the Simplex that can be separated with just 4 inequalities, whereas we know that the true value of the relaxation complexity in dimension 4 is 5. What do I mean exactly? So we could show that if we have all the infeasible coordinates or possible values of the coordinates in the first 3 dimensions, and we have a bounded value for the entries in the 4th component, then this set can be separated from the Simplex using just 4 inequalities. And in fact, this result does not only hold in dimension 4, we could generalize it in arbitrary dimensions, and we could show that if we want to separate a finite set of points from the d-dimensional Simplex, then roughly d/2 inequalities are sufficient to do so. This, of course, is not an answer to the question of Keibel and Weltke whether d+1 is the right number, but at least this result shows us that if we want to come up with a proof that it is d+1, then we cannot, cannot be based on finite sets Y that we want to separate from the simplex. The reason has to be that there exist infinitely many points at an infinite distance of the simplex, so to say, that we need to characterize to find the correct value of the relaxation complexity if it is bigger than this number. And with this, I'm at the end of my presentation. Let me quickly summarize what we've seen and maybe also some open questions. We have seen that under certain circumstances, we can compute the relaxation complexity. For example, if they admit a finite certificate, but in general, it is not settled whether we can actually compute this quantity of the relaxation complexity. This is only known up to dimension 3, where Avakov and Shimura came up with an algorithm to do so. But the algorithm that they propose has potential super exponential running time. And we are wondering whether we can do it at least in exponential running time. And then we have seen that this lower bound RC box can characterize the relaxation complexity if we have a finite certificate certifying this lower bound. But we have seen that the simplex, for example, does not admit such a finite certificate. And I think it's a nice and interesting open question to characterize the set of integer points that admit such a finite certificate. If you want to find the details, our print is available at Optimization Online and will soon be available on arXiv. And if you want to find out about the relaxation complexity of your favorite set of integer points, our code is also available on GitHub. Thanks for your attention.